Okay, today we're going to begin our discussion of Chapter 3, Fluid Statics. As the title suggests for this chapter, we're going to be looking at fluids that are at rest. This is not fluid dynamics yet, this is fluid statics, so all the fluids that we are going to be considering will be under a force equilibrium, and therefore they will not be moving. And I wanted to take this opportunity to, again, state the learning objectives. I do want to mention that this is a difficult chapter. It starts out fairly easy. I would say sections 3.1, 3.2, and 3.3 are reasonable, but then it gets quite difficult. Section 3.1, we're going to define pressure, various types of ways of referencing pressure, gauge, absolute, and vacuum, and then we'll talk just a bit about pressure units, although we've already done some of this. In section 2, we will introduce a concept called hydrostatic equilibrium, or the hydrostatic differential equation, and this is going to describe the physics of hydrostatics and the meaning of the variables that appear in the equation, and we will learn how to apply the hydrostatic equation to various problems. In section 3.3, which we'll do in a different lecture, this particular recording will just be to this point, sections 3.1 and 3.2. But in the future, we'll look at instruments that measure pressure, and we will come up with a general equation called a manometer equation, which will allow us to look at fluid measurements. Then it gets pretty tough when we start to talk about center of pressure and the hydrostatically equivalent forces. This allows us to start applying the forces on panels. An example, and we'll come up with a set of panel equations to predict forces and moments. An example problem of what I mean by a panel is a gate that may need to be opened at the bottom of a dam under extreme pressure, and what the forces are on a gate, and what moments and forces we need to apply to get that gate open to allow water to spill through the bottom of the dam. In addition, after talking about straight surfaces, we'll apply panel equations to curved surfaces, and these are hard sections. We will also describe the physics of the buoyancy equation and the meaning of the variables that appear in that equation, and learn how to apply that. This concept is very important as well for fluid statics. And then we will have a short section 3.7 to determine floating objects that are either stable or unstable. Now, a great example of this is just last fall. If you remember, this was the fall of 2013. They were able to basically take the cruise ship that wrecked off the coast of Italy, that was grounded off the coast of Italy. They were able to pump air into some tanks. They welded some tanks onto the side of that ship and then pumped air into them to make the ship buoyant again, and were able to get that ship off the rocks. And so that's a great example of creating a stable buoyancy situation in being able to move that large ship. So let's get going. What is the central principle behind hydrostatics or fluid statics? It's really the hydrostatic equilibrium. And this is an extremely important concept to understand. So this particular slide has a number of important things. In statics, because the fluid particles are not moving, each fluid particle is going to be in force equilibrium. That force equilibrium is shown by these diagrams down here at the bottom. But basically, let me just state what we have. The net force due to pressure, which we'll talk about in a minute, must equal the weight of the fluid particle. If these weren't balanced, the particle would start to move. The next thing that's very important to keep in mind throughout this throughout the entire semester is that the pressure force is compressive. So I'm going to add a couple of arrows to this. You'll see in this in this diagram, we see some arrows coming from the bottom and arrows from the top, but what it doesn't show are arrows from the side. And so there are arrows coming in to the sides as well. Turns out that they're balanced, and so there's no net force. The compressive force from the left and the right are balanced, and so there's no net force in either direction, so the fluid particle isn't moving. But the pressure, the compressive pressure coming from both sides, is balanced on this particle, and so it's not moving. Now the thing to note here is that the arrows on the bottom are larger than the arrows on the top of the fluid parcel. That's because the pressure on the lower part of this parcel, the lower boundary of this particle, this fluid particle, is greater than the pressure at the top. And so it's very important to note that that gives you a net force. There is a net force due to pressure. But when everything is in hydrostatic equilibrium, this net pressure force upward on the particle is balanced by the weight. And that's what we mean by hydrostatic equilibrium, that those two forces must be equal. So if we go on to define what pressure is, we've talked about this before. We know that it's really the magnitude of a normal force. If we look back here, the force is always normal on any of these surfaces, and because it's compressive. So it's always normal. This will be important when we use the momentum equation later on in the semester. I think it's chapter 6 or 7. So the magnitude of the normal force now is per unit area at a point in the fluid is going to be equal to the pressure. We know that this is force per unit area, and we now have a sense that this is going to be different as we go down in a column of fluid, that the pressure is going to be getting greater and greater and greater as we go down in the fluid. And that this is going to need to be balanced by the weight of the fluid parcel. The other thing to note is that a lot of times we like to talk about atmospheric pressure and things being relative to atmospheric pressure, and we'll return to this in a minute. But we always need to remember that if we have a free surface, that is a surface of fluid that is open to the atmosphere, that we will have atmospheric pressure basically pressing down on the top of that fluid. So there's different ways to reference pressure. And the first is through what is called absolute pressure, and this is relative to zero pressure. And the only situation where we can get zero pressure is when we have a vacuum. So a vacuum is a situation where there are no molecules. And so that is going to be a place where it's defined as zero pressure. This is kind of similar to the absolute temperature scale that we define Kelvin, where absolute temperature is zero when all molecular motion stops. So we'll have zero pressure when there are no molecules in the volume that we're considering. So that's absolute pressure. And for instance, atmospheric pressure is relative to atmospheric is an absolute pressure. But gauge pressure now is actually relative to the local atmospheric pressure. This makes our calculations easier sometimes when we're able to state that the pressure on top of a fluid, that's at atmospheric pressure, if this is a container of fluid, sometimes, a lot of times we'll want to say that this is zero pressure, say PSI gauge or Pascal's gauge, absolute pressure. It is not absolute pressure, it's gauge pressure, and we define it to be zero even though the actual atmospheric pressure is pressing down on top of this. So gauge pressure is relative to the local atmospheric pressure. Vacuum pressure, on the other hand, is going to be also relative to atmospheric pressure, but it's going to be positive if the actual pressure is less than atmospheric. So this is maybe a little bit difficult to say in words, so let's look at a diagram. First of all, note the definitions here at the top. where we have the gauge pressure is the absolute pressure, the actual measurement that we might be making, minus atmospheric. So as I said, if we, a lot of times we'll choose at the top of a free surface, we'll choose the gauge pressure to be equal to the atmospheric pressure. So, or we'll choose the gauge pressure to be 0 because that would make it equal to atmospheric pressure. And the vacuum pressure now is just kind of the flip. It's the atmospheric pressure minus the absolute pressure. So this would be our pressure measurement. And as long as the pressure measurement is smaller than atmospheric pressure, we get a positive vacuum pressure. And it's important to note that vacuum pressure is just the minus of the gauge, and the gauge pressure, which we can see from the equations, from these equations up here, that these are just have a minus sign in them. So if we look here at the diagram, let me choose a red pen so it's a little bit easier to see. We can see that the atmospheric pressure on this set of pressures, atmospheric pressure is right here. It's actually 101 kilopascals. If we went out with a barometer on that day and made a measurement at this location, we would get 101 kilopascals. And that is defined, that is the atmospheric pressure. So the absolute pressure minus the absolute pressure, the absolute pressure minus the atmospheric pressure is going to be 0. So the gauge pressure at that local atmospheric pressure is 0. So if we had a situation where we had a tank of air or something where we actually pressurized something to 200 kilopascals above atmospheric pressure, that would be an additional, it would be 200 kilopascals gauge, and it would be 200 kilopascals above this point here. But note that it actually is a 301 absolute, because we have 101 kilopascals here. This is not to scale, by the way. That's an A, kilopascals. Just a second. Kilopascals up to this point, and then we had an additional 200 kilopascals here, pascals. And so this total pressure equals 101 plus 200, which is 301 kilopascals. So from 0 absolute pressure down here, when we measure that gauge pressure, we have to add atmospheric pressure to it. Okay, so we kind of have an idea of what gauge pressure is, and that's what we normally use. Now there's one other complication, and that sometimes we use a vacuum pressure. And we can see that this pressure level right here, pressure B, is actually 7.25 psi vacuum. And that's a positive pressure because that pressure is actually less than atmospheric. Note that that also is minus 7.25 gauge because of this expression right here. The gauge pressure and the vacuum pressure, kind of the opposites of each other. So as long as we have a pressure that's less than atmospheric, as we do in this case of B, it's going to have a positive vacuum pressure. It's basically a lower pressure than atmospheric. And so so that's really it. We can see that we've got a definition of the gauge pressure being greater than atmospheric pressure. This is the atmospheric pressure, which is relative to 0 here, the absolute scale, and we have a vacuum pressure, which is less than atmospheric. All right, so the other thing, there's another subsection in the book, kind of switching gears here. There's another subsection of the book that talks about hydraulic machines, and basically at the bottom here, we have a hydraulic machine that's defined here, and this is very similar to a lever arm that I'm sure you've seen in either your statics or your dynamics class, some sort of mechanics class. I'm sure you've had this. So a mechanical advantage in general is defined as being something where you have an output force divided by an input force, and obviously you want this thing to be positive, and greater than 1. Otherwise you're at a mechanical disadvantage. So you want this thing to be greater than 1. And in the case of a lever arm, we see here that the output force we're interested in is F2 here at the end of this bar, and we're applying a force F1 over here at the where we have the long end. And this is just equal to L1 over L2, where L1 is the total length of the rod, and L2 is just the length here from this pivot point out to the end of the rod where F2 is going to be applied. And as long as L1 is greater than L2, we're going to be in this situation where our mechanical advantage is greater than 1. And then F2 will have an advantage. So there's a similar type of thing with hydraulic machines. And here we have a fluid, some sort of hydraulic fluid, inside a closed chamber. And the mechanical advantage here is very similar. It's just the output force over the input force, as we saw in general. But now it's simply equal to the area of this area over here divided by this area. And so as long as A2, this area here, is greater than A1, we will have a mechanical advantage to our hydraulic machine. And this is a simplification, assuming that we have a circular area, that these are our circular areas, which they normally are. They're usually pipes, and so or conduits. And so this is all predicated upon Pascal's principle, which says that if you cause a pressure increase somewhere, say by pushing down this piston at F1, then there is going to be a pressure increase at any point in the confined, if there is that pressure increase in the confined fluid will cause an equal increase in pressure everywhere else in the container. So basically if we increase the pressure here, we're going to increase the pressure over here too. And remember, these are normal forces. So, so let's take a look at an example here of a mechanical advantage machine here, a hydraulic jack. So we have a hydraulic jack that has the dimensions shown, and we can see that we have 2 types of mechanical advantages. We have the lever arm here that we're going to work that's at this pivot point, and the total length of the rod is 33 centimeters, and then we have this basically this pivot point at 3 centimeters. So we're going to get a mechanical advantage out of that. And then also we have a 1.5 centimeter diameter pipe here feeding into a hydraulic fluid, which is pushing up on a 5 centimeter diameter rod up here, or piston. So we would put our load here, and we're trying to determine how much, for a given force F, how much force we are going to be able to realize over here at F2. So let's take a look at that. So grabbing a new slide here. So to define the situation or state the problem, we really given F, applying F to the rod, to the machine, the hydraulic machine. What is F2 through that machine? That's really a brief statement of the problem. And what are we given? We're given all the dimensions of the problem. And we can look at that, but we're also given that F is going to equal 100 newtons. That's applied to the jack handle. And we're supposed to assume that the weight of the lifter is negligible. That's in the statement of the problem here. The weight of this lifter is negligible. So we're going to assume that as well. And we should probably write that down. If this was a homework problem, we should definitely write this down. So assume the weight of the lifter equals 0 newtons. That's 0 newtons, not on. 0 newtons. So our goal for this problem, obviously, is to find F2 and what load the jack can take. So if we think about this, if we're going to take action, we need to do two steps. We first need to, one, determine the force, what I'm going to call F1. Determine F1 at the lever arm. That's really the force on the plunger, because you'll notice this is F here. F1 is going to be applied right here, and then we'll use F1 and F2 to determine the advantage of the hydraulic machine. So let's do that first. Let's determine what F1 at the lever is, and that's going to be just this. F1 over F, using the mechanical lever advantage, is just going to be L1 over L2. And this is just merely 33 centimeters, the total length of the rod over 3 centimeters. So this turns out to be, we can solve for F1. This is, these units cancel and we're left with 11. So that jack handle gives us an 11 times mechanical advantage, and we know that F is 100 newtons. So we know that now F1 equals 1100 newtons. So we get a factor of 11 out of that. So the second point of action that we need to take is to determine the mechanical advantage of the hydraulic machine. So in that case, it's again very simple. We're just taking F2 now over F1, and now we know F1, and that is just merely the difference in the areas. And the difference in the areas, since they're diameters, is going to be pi 5 centimeters squared, that whole thing squared, over pi 1.5 centimeters squared. All right, so now we can cancel the pi's, and we can see that the units are going to work out nicely for us, but we'll write this out here in a second. This is going to be 25 centimeters squared, and 1.5 squared is 2.25. And we see that these cancel out, and as before, this should just be a number. So now if we solve for F2 directly, it turns out that 25 over 2.25 is just a little bit more than 11. It's 11.1. And this is now going to be times 1100 newtons, because that's what F1 is. And that gives us 12,222 newtons, or as the book shows, 12.2 kilonewtons. So we see that we have, this problem has given us an advantage of basically 11 times 11, or a factor of 12,000 in that hydraulic machine. And the central principle upon which the hydraulic machine worked is right here, the hydraulic fluid. Oops, the hydraulic fluid. And when we applied a force over here at B, or F1, when we applied F1, the pressure inside that fluid was constant. And so the pressure that we realized over here, we could also realize over here. So this Pascal's principle was very important. Pascal's principle.